All right, we're back again talking about network technology. So we haven't really moved on from that. I kind of got abruptly interrupted there. I had to leave in the middle of talking about network technology. I was kind of trying to keep everything as topic videos, but this is network technology part 2. But we're going to just continue on where we left off. I'm not going to call it chapter 3, part 2, part 1, and then part 2. No, I'm just going to keep going. So you guys will see that when you see them uploaded. But we left off, we were discussing the previous slide here. We were talking about Ethernet. Where were we? Where did we actually leave off? Okay, we were talking about broadband and baseband signaling. I'm not going to repeat what I went over there in part 2, but let's move on to Ethernet networks. Okay, so Ethernet is definitely the most common LAN technology, and actually that being said, 802.11 wireless and Ethernet, they work together hand in hand. In fact, some people consider 802.11 wireless an extension of Ethernet. So you could argue that Ethernet is the most popular LAN technology, and 802.11 wireless is just an extension of that. There's good reason for Ethernet being the most popular technology. The reason why is because of I would say the cost involved. Yes, that's one aspect, but I think the development of it was really well thought out. Whenever any new technology was added to Ethernet, so whenever any improvements have been made to the Ethernet technology, so for instance, we started with Ethernet bus, a physical bus, right, where everything was daisy chained together through a coaxial cable, and they developed repeaters so that you could connect multiple buses together, right? So this was the initial development. So if you think about the progression, we had Ethernet bus, and this would have been a physical bus, okay, which developed into, okay, so that's our first starting point with Ethernet. It started with Ethernet bus, right? Okay, and it was literally a daisy chain and it had terminators on the end. Okay, so Ethernet bus, daisy chain with terminators on the end. Collisions could occur. Okay, on that daisy chain. And the biggest competitor with Ethernet was Token Ring. So Token Ring was the other LAN technology in that day. Token Ring took Ethernet bus and sort of the principle of that and finished the bus, so it looped the chain back. So a physical ring would loop the chain back, and then it would only allow one device to transmit at a time, rather than using media access method. Oh man, my spelling. Of CSMACD, which is what an Ethernet bus would use. Okay, it would use a token ring, would use what was known as a token passing, was how it did its media access method, meaning only one device. So the analogy I give is like a talking stick. So if anybody here has ever, or if anybody in the class has ever been to a camp, you maybe were sitting around a fire, you know, at the end of a long day of camp, and maybe you were telling scary stories, and if it was like my camp experience, you had a counselor who would, when it was your turn to give a story, you got the talking stick, and if you had the talking stick, you were the only one able to talk. Nobody else was allowed to interrupt or interject. It was like, no, you don't have the talking stick, So-and-so is the talking stick, they're the ones talking. And that's how token passing works. Whoever had the token at a given time, they'd be the ones able to transmit. So the reason why this was the biggest competitor is it eliminated the possibility of a collision occurring on a token ring network. Okay, so the biggest competitor, Ethernet bus, collisions could occur, but transmission happened a little bit quicker because for the most part, they would use CSMA-CD as their media access method to listen to the line and make sure nobody else was talking. And then if a collision did occur, they would retransmit. And so collisions were relatively common back in the days of the Ethernet physical bus, right? And so the evolution, it progressed, and we still had, so let me just throw the word physical in here so you can kind of see. And I'm going to throw one more thing in here. It was half duplex. Okay, so there we have it. Ethernet bus. There's a daisy chain, terminators on the end, collisions could occur. The media access method would have been CSMA-CD, and half duplex would have been in place. Okay, so let's sort of draw a diagram here so that we can see it. Okay, this would have been our daisy chain. Okay, something to that effect. You see we have 3 PCs here in a line, and then on these ends I've got little dots on the end of my lines, and those circles represent a terminator, okay, which is a resistor that kills the signal so that there's no signal bounce. Okay, so that was the Ethernet physical bus. It progressed in that at some point somebody said, hey, let's create a repeater because these buses, of course, can only go a maximum 30 devices. And a total cable length of 185 meters. So if we throw these repeaters in there, that will help with the problem of signal degradation, which is what happens over distance. And when each network interface card along the way is reading the signal, it's affecting the ability for the signal to be transmitted. So the next step in the evolution of Ethernet as a technology, and sort of the reason why it beat out token ring, is because you were able to grow your network. It became scalable. So scalability was an important aspect of Ethernet networks that token ring networks did not have. With the advent of the repeater, scalability was added into Ethernet. So now we still had an Ethernet physical bus, but now with repeaters that allowed for scalability. Okay, so let's take a look at the paper there. Ethernet physical bus with repeaters that allowed scalability. So all of the same things, you still had your daisy chain, still had to have terminators on both ends, collisions could occur, CSMA-CD, half duplex, all of that was still the same. So all of this was still the same, but now you had the added scalability. So if I draw a little diagram, let's just assume that each one of these PCs represents 10. So now it would go into a repeater. Okay, this right here is our repeater, and on either end we would be able to go into a new daisy chain. Okay, so we could scale our network. Oops, there we go. So with the advent of repeaters, we still had a physical bus, but you can increase the size of your network. So this was a big revolution for Ethernet, and one of the big reasons I would say why it beat out token ring was because of scalability initially. Okay, so there was less collisions, less errors that occurred in token ring because of the token passing that I mentioned, the talking stick that prevented multiple devices from transmitting at the same time. Nothing actually prevents multiple devices from transmitting at the same time except CSMA-CD attempts to. It's not foolproof, of course, but it detects if a collision occurs. That's what the CD portion of it is. It detects if a collision occurs and attempts to retransmit after a collision. So Ethernet is evolving now, and we're getting closer to what we have today. So the next iteration was the logical bus. So now somebody gets the bright idea, they go, forget this repeater thing, that's great and all, but the daisy chain, it's still a huge limiting factor. So why don't we eliminate the need for a daisy chain any longer and move to an Ethernet logical bus? And it still has scalability, but this is now we have, instead of 2-port repeaters, we have multi-port repeaters known as a hub. So now you gain scalability, but you also gain the benefit of the physical star, which is a central management point, central control. Okay, so scalability and central wiring. So now it's a logical bus, but a physical star. So Ethernet is evolving, okay? We see sort of the progression. We started with an Ethernet physical bus, literally a daisy chain, continue with the daisy chain, but now it's scalable because of repeaters. Okay, and finally, we're moving to the Ethernet logical bus, where now we no longer have a daisy chain, so daisy chain is out. All this other stuff is gone. Terminators are out. There's no need. All that's done with the central wiring of your hub. The hub includes the terminators on either end internally. So when we go back a couple of slides, if you reference back a couple of slides in actually the previous video that I made, you can see what that means, what that involves. So you actually see inside the hub. If you look inside of a hub, I'm going to draw a hub here real quick. Our daisy chain is inside of the hub. Okay. So each one of these would be a port on the hub, and you see there's a sending and a receiving port. Okay, oops. And that would be your daisy chain. Okay, and so now when you connect out, okay, one more thing I should mention. Up until this point, our medium has been coaxial cable. So everything was the same between all of the physical bus, Ethernet physical buses, right? The medium has been coaxial cabling. Now we've also shifted our medium, right? So we've got PC, 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 PC. So logically, this is a bus, and now we're also we've changed our medium over to UTP, unshielded twisted pair. At this point, there is no fiber optic. Okay, fiber optic has not been included thus far, okay, with hubs. Okay, so we see Ethernet is evolving, right? And we now no longer have a daisy chain. We no longer need repeaters, but we have a central repeater that's a multi-port repeater and also known as a hub. Okay, so the next iteration of Ethernet, we're getting closer to what we actually use today. One more thing. So we max out our speed here. The maximum speed is 10 megabits per second in both of these designs. So 10 megabit per second. Okay, maximum speed. Oops. There we go. Maximum speed, 10 megabit per second. Clear over until we get to right here, and then our evolution takes another big important step. So this was a big important step in the evolution of the Ethernet technology. Okay, the central device, now making it a physical star, logical bus, was a big deal. but also the ability to do multiple speeds. Now you're dual speeds. You can do 10 or 100 megabits per second. Okay, so now we're able to get higher speeds, 10 or 100 megabits per second, because of hubs. Okay, we're still operating half duplex. Okay, and we're still dealing with bandwidth sharing, so that 10 megabits or 100 megabits is shared among all the devices, but we're not quite done with the evolution yet. So the next leg of this evolution is Ethernet logical switched and physical star. Okay, so now the central device gets an upgrade. When you're over here, when you're over here, it's just a dumb device. It receives a signal on any port and it forwards out all other ports, right? That was neat. That was handy. It was very, very cool. It made it so that we could move away from the physical bus into a logical bus and a physical star. But now we need to do one more upgrade that's going to really revolutionize this thing, and that is changing the logic of how data is transmitted. So the logical topology of how data gets from point A to point B, and that's where logical switched comes in. So now we're using as our central device a switch, okay, which, if you remember, creates a dynamic connection. Okay. Okay, so that's our central device. We have a switch now. So we've moved over. We're now dealing with logical switched, physical star. Okay, Ethernet is evolving. So now we're capable of creating only the connections that are necessary. So we eliminate, first we add the capability of full duplex, meaning devices can send and receive at the same time. In fact, multiple devices can send and receive because they're not on the same logical bus. Okay, so device A over here could transmit at the same time as device D down here, and they would not create a collision. Okay, there would be no collision in this case because we're not dealing with a logical bus anymore. We're not dealing with a bus of any kind. We're dealing with logical switched. So the connection, so let's suppose device A is trying to send to device C, and device D is trying to send to device, oops, screwed up my drawing here. Okay, sorry, hopefully this is legible somewhat. Okay, so the connections are only generated, they're only created when transmission is occurring. So we see we have A, and that's sending over to C, and we have D, and that's sending over to B. Okay, so these devices are able to send at the same time because the switch is able to handle multiple incoming streams of data at the same time. Okay, it's not going to send now in half duplex if this is still operating in half duplex. So part of the brilliance of Ethernet is there is always a built-in backwards compatibility. So you could use a logical bus in combination with a logical switch. You could use these in combination with each other. Okay, so that was part of the beauty of Ethernet technology, is it always built in some level of backwards compatibility. And so there was still half duplex available. So a collision could still occur if it was in half duplex and you had the switch, the central device, sending at the same time, transmitting at the same time as your PC. So if we have a transmission occurring on this line at the same time, boom, a collision could occur on the line in half duplex mode, but not in full duplex mode. And full duplex eliminates collisions from the equation altogether. Logical switched, full duplex, collisions become a thing of the past. So Ethernet is continuing to evolve and get better. So the big competitor with Ethernet was, of course, Token Ring. And Token Ring they were able to brag and say, "Ha, we don't have collisions." Okay, even though that's not necessarily true, they did have some collisions, but it was much more rare than with an Ethernet physical bus. So now Ethernet's evolved and they've developed a technology that says, "Ha, we don't have collisions either. Collisions are removed from the picture with full duplex and with logical switched." Okay? And the other big development in Ethernet was 10, 100, 1000. So pretty much anytime Ethernet adds a new speed, they always include backwards compatibility with old speeds. So if you still have an old computer with an old network interface card that's running 10 megabits per second and half duplex, it will function with a brand new gigabit Ethernet switch, or 10, 100, 1000 switch. So the underlying technology has stayed the same, and this is sort of where we are today. The only real changes now that are happening, we still use logical switched, but the only real changes that are happening now is the increasing of speed. And so that's where we get to our slide. If you look at our slide, you see there's a broad range of support for speeds, 10 megabits to 10 gigabits per second. Okay, so Ethernet technology is by far the most popular. Token Ring is really the only other one, and really a lot of people would argue that 802.11 wireless, even though it's very popular, it's actually just an extension to the Ethernet technology. And we're going to look at Ethernet frames and how they're consistent among both. So, but there you see, basically I've broken this down so that it's a little bit clearer, but you see it can operate in a physical bus or physical star, a logical bus or logical switched. And for my chart here that I drew up here is the breakdown of that. So we've got two charts that break that down. I'm not gonna continue on with that, but I just want you sort of grasp the evolution of Ethernet as a technology and see sort of why there's a lot of backwards compatibility built in. So that's probably the biggest reason why there's such staying power. Okay, so Ethernet addressing works like this. We know that each network interface card, sorry about that. Each network interface card has a burned-in address. We've talked about that. Okay, network interface cards thus far, everything we've talked about has been referring to Ethernet as the underlying technology. So each network interface card has a MAC address, which is the burned-in address, and it's expressed, we've talked about these, it's expressed as 48 bits, but usually expressed for us, for our purposes, as hexadecimal digits. In order for a NIC to receive an incoming frame, it must match the NIC's burned-in address, or be a broadcast. Okay, so it would have the broadcast address in the frame's destination MAC portion. Okay, so once a frame is processed by a NIC, it sends it up, obviously, to network protocols. So we've discussed this when we talked about NICs, so let's move on from that. Okay, there's 4 different Ethernet frame types. This was for allowing compatibility with different network protocols, but the only network protocol that's really in use today is TCP/IP. That's the protocol suite that has beaten the day, just like Ethernet is sort of the LAN technology that's won the day. TCP/IP is the network protocol that's won the day. Back in the day, there was a lot more. In early networking, there was a lot more. There was really 4 major different protocols that were sort of vying for position. But we know IP, Internet Protocol, this won the day. And I think a lot of that had to do with the ability for backwards compatibility built into any new upgrades to it. So let's look at a Ethernet frame, completed Ethernet frame. Some information about it is Ethernet Type 2 type is going to be always included, even though it's not really necessary anymore, because other network protocols aren't really common. You still always have a frame type. So if you look at the portions of a completed frame, we have the frame header and the frame trailer. The header is comprised of a total of 14 bytes. okay? 6 bytes for the destination MAC address, or 48 bits, 6 bytes for the source MAC address, and 2 bytes to distinguish the type, okay? 4 types, 2 bytes to tell you 4 types, okay? Pretty much all frames, though, are going to be type 2. So you see Ethernet II, Ethernet 2, frame type is used by TCP/IP. So that's what going to be most frames are that are in use today. And then you see the data. This would be everything from packet to the chunks of data that are being broken up for transmission. So if we look at it, so I'll draw this up so that we can see it. I've got the graphic here, but I want to sort of divvy it up. So oops. A better way of putting it would be to say that in this portion we have the packet. Good way to put it, I guess, frame payload. This is what's actually being delivered. So by the frame. The frame is delivering this information here, this payload. Okay? And then at the very end we have a trailer. The trailer, FCS stands for frame check sequence. You'll often see it written as CRC. CRC is the name of the algorithm that's run. Frame check sequence is more of a general term. CRC is the name of the algorithm. CRC stands for cyclical redundancy check. Basically, that's just for error checking. If there's a problem with the frame, then whatever math happens here, whatever 4 bytes of information are here, will be the answer to essentially a complex algorithm that takes into account the data and the frame header and all the information in the previous parts of the frame. So if one bit gets inverted or mixed up, the frame check sequence will fail. So 1 bit gets corrupted in the entire frame. We're talking 1518 bytes, so times 8, that's how many bits there would be in the largest frame size. If one of those gets screwed up, the frame check sequence is going to say, nope, no good, and discard. So the NIC on either end is what runs the frame check sequence. And actually, in some cases, switches will also run the frame check sequence. But that's the completed information. A frame is between 64 and 1518 bytes, and that's because the minimum packet size is going to be 46 to 1500 bytes total with the packet header and everything in there. So when you add the 18 bytes of frame data, that's where you get your maximum size, your 1518 bytes, or your minimum size, 64 bytes. Okay? So there you have that. Okay, that's that. We're moving on. So now, Ethernet media access. So how it accesses the media. I haven't talked about CSMACD. Okay, I mentioned it previously, but I thought I'd already discussed it. So sorry, I did. This is the 3rd time I've done this lecture today. So 2 other classes, actually this is just the 2nd time I've done this lecture today. So I have one other class that I teach this same information to. So I apologize. I did not mention CSMACD yet. I mentioned it briefly when we talked about the evolution, but now I'm going to actually tell you what it is, so I apologize. So media access method, these are the rules governing how and when the medium can be accessed for transmission. So I talked a little bit about the 2 common types, token passing and CSMACD. Those are the ones that were competing and vying for position. Of course, we talked about how Ethernet won the day and token passing did not. But CSMACD, to break it down, carrier sense, CS, carrier sense, this means listening before sending. So the network interface card that's getting ready to transmit data, if it's an Ethernet NIC, it will listen to the interface. It'll listen to the medium. Okay? It's going to listen to the medium for a transmission. If there is no transmission, then and now you got to think in terms of this was in the days of physical and logical buses was when this was utilized. Okay, CSMACD was utilized by physical and logical buses. Okay, so the listen before send, it must hear silence before it can transmit. Multiple access means if two or more stations hear silence, multiple stations can transmit at the same time. If that occurs, that's not good, because then a collision will occur. And so carrier sense multiple access means it's going to listen for silence, and if it hears silence, it's going to transmit. But if silence happens, right, multiple access, multiple devices transmit at the same time, a collision will be detected. That's where collision detection comes in. Okay, so collision detection. If two or more stations transmit and a collision occurs and is detected by the NIC, meaning, so what a collision is in a nutshell is on a bus, we have a wire with 5 volts running in either direction on the bus. Okay, here's our wire. Okay, and at some point, that 5 volts, if it's positive 5 volts in either direction, because the data is traveling in both directions, that 5 volt is going to increase to 10 volts. Right? We're talking baseband here. Ethernet always uses baseband. That's going to go up to 10 volts, and it's actually going to go both directions as 10 volts of data. 10 volts is useless. 10 volts is useless data. It cannot be read. It cannot be interpreted by anything on the line other than as a collision. So if the NIC detects a collision, it's detecting 10 volts on the line. And so what happens is with CSMA-CD is it listens for no transmission. If it doesn't hear anything, it begins its transmission, and then it listens again and waits an allotted amount of time. The specific amount of time can vary depending on what it's sent. And then if it hears now on the line, it hears 10 volts, that it knows that a collision has occurred. It detects 10 volts, knows that there's a collision. So it stops. Both stations that have transmitted will stop. They'll wait using a random number generator. They'll generate a random amount of time, usually 100 milliseconds or so, within 0 to 100 milliseconds, randomly generated. One of them will begin to transmit first. Whichever one generates the lower number, it's the luck of the draw. At that point, one of them will begin to transmit first. So after that amount of time, it's going to listen again on the line, and it's going to see the other device is transmitting. So CSMA-CD was a pretty good way of handling collisions. That's the only time that retransmission occurs in an Ethernet network. Retransmission only occurs in the event of a collision. Okay, so Ethernet isn't concerned with data getting from point A to point B unless it detects a collision after sending. Okay, so I mentioned collisions. I sort of told you what they are, but so because anytime you're connected together on a logical or physical bus, all devices will see all transmissions on that bus. So the extent to which a collision will propagate is also known as a collision domain. So this is how far collisions will go on a bus. So it's the extent to which a bus is a bus before it gets to a switch, essentially. Once it hits a switch, connections are dynamic. They're no longer in place consistently like in a bus. Okay, and so when a collision reaches a switch, suppose we have a network here, and we have a hub here, a switch here. I wish I could. I'm going to figure out a way to do this on my screen at some point, I think. Do it quickly. Maybe get a drawing pad that I can use with the screen. So on either end, we have hubs. If you can't tell, it's arrows with another arrow pointing into it. That's sort of how you denote a hub. And then here we have a switch. Our collision domain, even if we have computers connected out, is the extent to which a collision will be propagated. If a collision occurs anywhere within this area, so if a device here sends at the same time as a device here, a collision would occur, and that would be seen by every other device connected to this hub. And so this hub up to the switch is a collision domain. We've talked about broadcast domains go to a router interface. Collision domains go to a switch port. Think about it like that. Okay? And So within a collision domain, all devices within that domain are subject to the possibility that if they send at the same time, a collision could occur. So if they send a frame, a collision could occur. Now with switches and full duplex, we know collisions are no longer possible. So let me draw another little network here. Here we have right here we have a switch. You see my switch there, and it's branched off to computers. Each one of these lines theoretically could be a collision domain, and so they're counted as collision domains. So all of my circles, those are collision domains. So if I were to tell you how many collision domains this particular network has, it would be 5, one for each device coming off of this switch. Okay, the reason why, because if the switch is in half duplex mode, there is the possibility that a collision could occur from here to here. So if the switch sends at the same time as a PC on this end, then a collision could occur on the wire itself. Okay, so that's why they still consider that a collision domain. All right, so you see this is, okay, so they've got a graphic in here that shows basically the same thing I just drew up. You see you've got your hubs all connected together. Even though there's multiple hubs over here and tons of devices, as far as this is a logical bus, that's your collision domains, because this is still on the same logical bus. You have to think about it in those terms. This is all on the same collision domain. And then over here you have your switch, so once you get to that switch, the switch will not forward the collision, but each hub will. So if a collision occurs on this network, or on this hub here, even just between two devices plugged into this hub, it will be seen by every device within the collision domain. Same thing over here, but the switch will not forward it. Okay, so some other, so the way Ethernet handles errors. Ethernet is considered best effort delivery, so there is no acknowledgement on either end. So, and actually there is further up when we talk about Ethernet functions at the network interface sort of layer of networking. Okay, further up at network protocols, we know that the NIC handles is where Ethernet occurs. Further up to the network protocols, there is some better error handling that will make sure that data is getting from point A to point B. But that's not handled by Ethernet itself. Ethernet, the only time a retransmission occurs directly at the network interface layer through Ethernet is in the event that it detects a collision immediately after transmission. Okay, within moments after transmission. Okay, so if a collision occurs, that's the only time retransmission will occur. But again, network protocols and applications ensure delivery. So that's where ensuring data gets from point A to point B is going to be handled further up. Okay. Ethernet does detect damaged frames as it goes along. So the cyclical redundancy check, which is part of the frame check sequence, it is at the trailer of the frame, is what verifies that a frame is undamaged along the path. So some switches will run the CRC on a frame when it receives it, but not all. Usually, but it will always be done, I should say, by the sending NIC and the receiving NIC of that frame. So the NIC that it's destined for is going to run the CRC, and I guess the sending NIC is what develops the actual algorithm for that frame. It doesn't actually run the CRC before it sends it. It just develops it, creates the algorithm. I guess so that's part of running the CRC. So it runs it to generate the number and then sends it on its way. And then the receiving NIC will definitely run it again to verify that the frame is not damaged. Okay, if it is damaged, all it does is it discards the frame and then just says good riddance, right? If a NIC receives a damaged frame and it runs, so it receives a frame and it's damaged, it runs the CRC, verifies, realizes it's damaged, it doesn't do anything with it other than discard it. Okay. So I mentioned full duplex and half duplex. I've talked a lot about this. I've already even, I think, mentioned the analogy of half duplex being like a two-way radio. If I have two-way radios and I have my little brother go into the other room, if I had a little brother, and I want to talk to him, I say, breaker, breaker, 1-9er, right? He'll hear it, but as soon as he starts to press the button and talk to me, a collision occurs and actually neither one of us gets the transmission. Okay, that's half duplex in a nutshell. It's like a two-way radio. Okay, full duplex is more like a telephone or a cell phone, right? If I'm talking on my phone, I can be saying things at the same time that I'm hearing things on my phone and actually receive the information that's being transmitted, even though I might be transmitting at the same time. So I can be transmitting and receiving at the same time. So most switches operate in full duplex by default. Of course, I mentioned that Ethernet has a lot of backwards compatibility built in. So full duplex or half duplex is going to be generally automatically determined based on the NIC and the switch and what they're capable of. Okay, so but most switches operate in full duplex mode. Okay, so we're just going to power through these. Actually, you know what? I will show you those just because you can pause and see a few of the quiz questions. So, but that's the end of this video. It's about 40 minutes long, and I'm still not done yet. So buckle up. We've got maybe 1 or 2 more videos, and then we'll be done with chapter 3.